Hi everybody, let's get started with the part 2 of this video series and in this video I have discussed the concept of an electric dipole. Now when we talk of an electric dipole simply is a plus charge and a minus charge which are separated from each other by some distance. Now in most cases, students make a mistake in understanding the concept of electric dipole. See, when I said electric dipole, I said it is a plus and a minus charge which are separated from each other. So, is it like I keep plus charge in one end of the room and the negative charge in the other end of the room and finally call it an electric dipole? The answer is no. Although they are separated, they have to be still connected by each other. It's like, say for example, take a molecule like HCl. So, if you take a molecule like HCl, we all know that chlorine is slightly more electronegative compared to hydrogen, and that is why it will pull the electrons towards it, and because of that hydrogen develops a plus delta charge and chlorine develops a slight negative minus delta charge. Now see, there is a separation of charges, but the two charges are still connected with each other because HCl by itself is a molecule and HCl is formed because of a bond between hydrogen and chlorine. So that plus delta and minus delta are connected to each other, and that is why we say this forms an electric dipole. So like I said, in an electric dipole, the plus and the minus charges are separated from each other, but in spite of being separated, they have to still be connected with each other. They have to be linked with each other for this to be called an electric dipole. Now the strength of an electric dipole is what we measure in terms of something called electric dipole moment. Now say for example, these were magnetic dipoles. Had it been North Pole and South Pole, I would have called this a magnetic dipole, but because this is plus and minus, I am calling it electric dipole. And like I said, the strength of electric dipole is what we measure in terms of electric dipole moment. Electric dipole moment, we will represent it with the notation P bar, and because I said P bar, this electric dipole moment will be a vector. That vector will be directed from negative to positive of the dipole. So the vector electric dipole moment will be like this. Now electric dipole moment is given by magnitude of any one of the charges. So say for example, this was plus q and this was minus q. So you just take the numerical value of the two charges. Now like I said, the charges have to be separated. So the plus charge and the minus charge are actually going to be the same in magnitude when I talk of an electric dipole. Okay, so you take the numerical value of any one of the charges as q and multiply it with the distance between the two charges. The distance between the two charges, if I call it d, you can write it as q into d, and some of the reference books, that distance they call it 2l. That is the distance between the negative and the positive charge. Instead of L, they write it as 2L. So instead of D, you might also be having the numbers as 2 into L. So you can also write electric dipole moment as Q into 2L. Like I said, some of the reference books might be writing electric dipole moment like this. In short, what you need to keep in mind is electric dipole moment is magnitude or numerical value of any one of the charges multiplied by the distance between the two charges. So this is what an electric dipole moment or an electric dipole means. Go ahead with the second point. Say for example, we take this electric dipole and we put it in an electric field. If we put it in an electric field, let us say the electric field intensity is here. This is an electric field where the electric field intensity goes like this, and we are putting our dipole like this, where this is the plus charge and this is your minus charge. We all know that when we put a charge in an electric field, the charge will experience a force, and the force that any charge will experience is given by F is equals to Q into E. This is what I had discussed in the part 1 of my video. In case if you have not referred it or you don't know this result, I have left a link in the description box below to the entire playlist. You can check out that video and then get back to this. So the force experienced by this charge will be plus Q into E, and because E and F are vectors, the direction of force and direction of E bar are going to be the same for the charge plus Q. So this charge experiences a force in this direction given by F is equals to Q into E. Go ahead with this charge. This charge will also experience a force given by F equal to, but the charge for this is not Q, it is minus Q. So F will be minus Q into E. If I write them as vectors, you realize that F bar and E bar are going to be oppositely directed because this was a minus charge. So if E bar was here, F bar, that is the force this charge experiences, will be on the left hand side. See, magnitude wise, this force and this force, they are the same. This was also Q into E and this is also Q into E. The negative sign only indicates that the force is in opposite direction to the first one. So ultimately the two forces, we say that they are equal, and because the two forces are equal, they will not try to move the dipole linearly. But if you realize, the two forces are actually having the ability of turning the dipole. Because this force is here and this force is here, the dipole is going to get turned like this. That turning effect which is experienced by the dipole tells us that the dipole experiences a torque. So second formula is for torque acting on a dipole in electric field. So you can write that torque as tau, and if you remember, the way we were giving torque, or the way we write torque, is the magnitude of any one of the forces multiplied by the distance between them. So we will say that the torque experienced will be magnitude of any one of the force, which is Q into E, multiplied by, we need the perpendicular distance between the two forces. If we just draw this line, you will realize that the perpendicular distance between the two forces is this. And let us say that the electric dipole or the electric dipole moment. Now electric dipole moment is a vector from negative to positive charge. So electric dipole moment will be a vector over here. Let's say that the vector between the electric dipole moment and E is theta. That is, let's say this angle is theta, which in other words tells you that this angle is also theta. Now if this angle is theta and this is the length that you require, you can apply the formula of sine theta in this triangle. So you will realize that sine theta is the required length, let's call it d, divided by the length of the dipole, and the length of the dipole we can write it as 2L. So d upon 2L is the value for sine theta. The distance between the two forces was d, this was d. So d can be written as 2L sine theta. So we have torque as QE multiplied by the distance between the two forces. We get it as 2L sine theta from here. And that is why we say that the torque experienced by the dipole is Q into E into 2L sine theta. But think over it. What is Q into 2L? If you realize Q into 2L is the electric dipole moment, which we can write as P bar. So this becomes Q into 2L becomes P. So we have P into E into sine theta. If tau is P into E into sine theta, if you remember, A bar cross B bar's magnitude was AB sine theta. If tau is PE sine theta, we realize that tau bar should be given by P bar cross E bar. And that is why we say that torque on a dipole in an electric field is given by tau bar, which is P bar cross E bar. P bar is the electric dipole moment and E bar is the electric field intensity of the field in which you have kept the dipole. Okay, so that's about torque acting on a dipole. And the third formula would be for energy of a dipole. Now let's consider the previous case only, that we are keeping a dipole in an electric field. So that's your electric field, and let's say that we are keeping a dipole like this. So this is where the plus charge of the dipole is and this is where the minus charge of the dipole is. We just learned that when you keep a dipole in an electric field, the dipole will experience a torque, and this dipole is experiencing a torque. Now where will the torque try to bring the dipole? If you realize that the torque is P bar cross E bar, P bar was a vector here, this was P bar, and this is your vector E bar. So if you realize P bar cross E bar, the direction of the vector torque will be inside, but that torque, it's P bar cross E bar, right? So the turning of the dipole will be like this. Okay, so the torque will try to turn the dipole from this position to this position, and when it is perfectly horizontal, the angle between P bar and E bar will be 0 because they will be parallel to each other. And when the angle becomes 0, that torque which was P bar cross E bar can be written as PE sine theta, and because theta will be 0, the torque experienced by the dipole finally in this position will be equal to 0. Okay, now let's focus on this energy of a dipole. Say for example at this position where P bar was making an angle of theta with E bar, that is the dipole was making an angle of theta with E bar. We are trying to turn the dipole against the torque like this. And let us say by applying a little torque, a torque which was slightly higher than this Pe sin theta. See, because we are turning the dipole against the torque that we apply should be greater than the torque which was trying to turn it here. The torque trying to turn it here was Pe sin theta. So we will apply a torque slightly greater than Pe sin theta, and that will make the dipole turn in the opposite sense. So let us say because of our torque applied, the dipole is getting rotated by an angle which is very small, which is d theta. So the work done by us will now be given by the torque we have applied multiplied by the rotation we created, which was d theta. And the torque we applied was just slightly higher than Pe sin theta. We will say it was approximately Pe sin theta only. So we have Pe sin theta d theta as the torque, as the work done in turning that dipole. Let us say we have turned the dipole from some initial position theta naught to some final position theta. So the total work done will be given by integration of Pe sin theta d theta from some initial position theta naught to some final position theta. So the work done will finally be Pe integration of sin theta is minus of cos theta. When you put in the upper limit theta, you get minus cos theta minus the lower limit, that is minus of cos theta. So we will have minus cos theta minus of minus cos theta naught, and that gives us the work done as Pe into cos theta naught minus cos theta. This becomes the final formula. See, whatever work you have done is the energy which is stored in the dipole as potential energy. So we say that the energy of a dipole is going to be given by Pe cos theta naught minus cos theta. So this is Pe cos theta naught minus cos theta. And now this is where certain different formulae keep arising. It is because, see, energy of a dipole depends upon the initial position. What if in this case I tell you that the initial position of the dipole was here and we are turning the dipole from here to some position theta naught? You will say initial position, if it was parallel to E bar, theta naught was 0, and if you put theta naught as 0, you get energy of the dipole as Pe 1 minus cos theta. This will also be the same as work done because it is we who are turning the dipole. Now say for example, instead of turning the dipole, what if initially the dipole was perpendicular to E like this? So if the dipole initially was this was E, and the dipole was this, with this being the plus charge and this being the minus charge, both of them well within the electric field, then the plus charge will experience a force here and the minus a force over here, and these forces by themselves will turn the dipole over here. So in that case, the energy of a dipole or the work done can be given by putting theta naught equal to 90, because initially the angle between P bar and E bar was 90. So when you put cos theta naught as 90, this becomes 0 and we get minus Pe cos theta. And you can write this as minus P bar dot E bar. So often, depending upon what condition has been given, you can use the formula for work done or energy stored or energy of a dipole as minus of P bar dot E bar or Pe 1 minus cos theta. Like I said, which formula to use depends upon the initial condition. In many questions, the initial condition is not given. So you need to try or you need to judge the question and then predict which would be an appropriate formula to use. For the time being, or as a general formula, the third one, that is Pe cos theta naught minus cos theta, is the one that you should remember. So these are some things about a dipole that you are learning. The next formula that you are learning is for electric field generated by an electric dipole. So say for example, you have an electric dipole with this being the charge plus Q, this being the charge minus Q. Let the total length be 2L. And let this be the center of the dipole, which is, let's just call it the origin. What if I ask you the electric field generated at this point because of the dipole? and this point from the origin or from the center of the dipole is at a distance of, let's call it x. The electric field generated at that point, now this point is on the axis of the dipole. This line is what you call the axis, and if you just draw a line perpendicular to the dipole passing through the center, this line is what you call the equator. Okay, so now I want the value of electric field generated at this point, which is at a distance of x from the center of the dipole. The electric field at that point will be generated by two charges. One is plus q and the other is minus q. The electric field intensity that the charge plus q generates over here is given by k into q upon r square. This was a formula that you have learned in the earlier video. Like I said, if you don't know this formula, do refer the previous video and then get back to this. It will help you in understanding these things in a better way. So the electric field generated by q at this point will be given by kq upon r square. K was 1 upon 4 pi epsilon naught. Q was the charge q itself, but r was the distance of that point from the charge q. The distance of this point from q can be written as x minus L. So instead of r, we will say x minus L the whole square, plus the electric field at that point is generated not only because of q, it is generated because of minus q also. And the electric field that minus q will generate over there will be given by k into the charge itself, that is minus q, divided by the distance of that point from the charge minus q, which will be x plus half of the dipole, and if full dipole is 2L, half the dipole will be L. So we will have upon x plus L the whole square. Try to just simplify that. So you will have a kq common outside. The denominator is 1 upon x minus L the whole square minus 1 upon x plus L the whole square. So this would become kq. The denominator would be x minus L the whole square into x plus L the whole square, which is x minus L into x plus L the whole square. That becomes x square minus L square the whole square. And in the numerator, when you have terms like x plus L the whole square minus x minus L the whole square, open the brackets, and when you simplify the terms, you will have 4 into x into L. Now for all calculation purposes, we assume that the dipole is a short dipole. So because it is a very short dipole, the value of 2L will be very small. If the value of 2L is small, the value of L also will be very small. And if L is very small, then x square minus L square will be approximately equal to x square only. So the denominator becomes x square square, that is x power 4. And when you cut an x and x in the numerator and denominator, you are left with k into q into 4L divided by x cube. Now keep in mind, q into 4L is actually q into 2L into 2, but q into 2L is again the electric dipole moment. So we write this as k into p into 2, that is 2 kp by r cube. Sorry, 2 kp by x cube. So that is the formula for electric field intensity E at a point which is there on the axis of the dipole. See, this is the derivation that I have shown you for one point. Of course, the derivation is important because you then realize how these formulae have come or how you can derive them. But remembering this is not the point. See, you can, because see, this is only one case. This is electric field intensity at a point on the axis. In a similar way, you can actually derive a formula for electric field intensity at any point on the equator. What you need to remember is the formula for electric field intensity at, in general, any point in the vicinity of the dipole. Say for example, I talk about equator. We wouldn't derive this, but I will still tell you the method. At the equator at this point, the electric field because of Q will go in this direction, because you have learned that a positive charge always pushes the electric field away from it, and a negative charge always takes electric field towards it. So this is a positive charge, it pushes electric field away from it, and that is why at this point the electric field because of plus Q will be here. Because of minus Q, the electric field will be coming towards it. Now because of symmetry, you will realize that these angles are the same. This angle, if this is theta, then this angle will also be theta. This vector can be resolved in two components. One component goes up, that will be, let's say this vector is k. Also keep in mind that because of this q, the electric field here will be kq by r square or kq by whatever that distance is. And because of this minus q, the electric field here, that will also be kq by r square only. So that kq by r square, let's call it some term like m. So if this is m, this is also m. The component of this going up is m sine theta and the component of this going down is also m sine theta. So the vertical components are cancelling out each other and the horizontal components, the horizontal component of this will be m cos theta and the horizontal component of this will also be m cos theta. So the horizontal components are getting added and that is why electric field on the equator will be in this direction. That resultant electric field will be 2m cos theta. So that is how you can find the electric field at the equator. But like I said, what you need to learn is a general formula. So in general, instead of taking any point anywhere, let's just take a point. Instead of taking random points like this, let's just take a point somewhere over here. And that point has been taken in such a way that if you join it with the center of the dipole, then this point, the line that joins that point with the center of the dipole, is making an angle of theta with the axis of the dipole, or you can say it's making an angle of theta with the dipole. The electric field intensity at that point will be given by Kp divided by r cube root over 3 cos square theta plus 1. It's just a formula that you need to remember. Now, if you are wondering that why to simply remember it, why not a derivation for it? Of course, there is a derivation for it, but that derivation is too long and for JEE mains it's not that helpful. So I am straight away giving you the formula. You can have a look at the derivation from any of the textbooks that you have if you want. If you don't want, remembering the formula will just work fine for you as far as the competitive exams and the MCQs are concerned. So that is the electric field intensity at, in general, any point which is at a distance of r from the center of the dipole, and that formula is Kp by r cube. So P is the electric dipole moment of the electric dipole that we have made. R is the distance of that point from the center of the dipole. K, like every case, is 1 upon 4 pi epsilon naught and root over 3 cos square theta plus 1. Theta is the angle which this line has made with the dipole, or you can say with the axis of the dipole. Okay. In a similar way, you can have a formula for potential at that point. The formula for potential is Kp cos theta divided by r square. Just a formula that you need to remember. Even potential, like the previous case, can be simply added. So if I take a point on the axis, say for example this point only, you can say the potential at this point because of q will be kq by x or kq by r, where that r will be x minus l. So at this point, if you want to check, v will be kq upon x minus l plus, because of this, it will be k into minus q upon x plus l. Just simplify this and you will get some expression where you can write x square minus l square approximately as x square, and if you just apply that theta as 0 in this formula, you will see that the formula becomes Kp by r square or Kp by x square, because the distance from the center is equal to x. Okay, so potential, the formula for potential has also been derived in the same way. That is, potential at that point, this point, will be the potential because of plus q plus the potential because of minus q. Simplify the formula and this is what you will have. So these are two formulae for electric field intensity and the potential generated by a dipole at, in general, a random point. So these are the discussions that keep happening around an electric dipole. One last thing, when we were talking about this, I need you to think two conditions where the torque on the dipole will be equal to 0. See, the torque on the dipole will be 0 if P is sine theta. If sine theta will be 0, then the torque will be 0, because tau is P is sine theta. So sine theta will be 0 if theta will be 0 or theta will be 180. Theta 0 means P bar and E bar are parallel to each other. So if the dipole is with a minus charge here and a plus charge here, in this case P bar and E bar are parallel and the torque will be 0. even if you interchange it, if the plus charge is here and the minus charge is here, the electric dipole moment goes from negative to positive. Now P bar is here and E bar is here. The angle between them is 180. Still the torque will be 0. But we say that this condition is a condition of stable equilibrium and this is a condition of unstable equilibrium. Unstable equilibrium and stable equilibrium. First of all, I am calling both of them equilibrium because the torque on both of them is 0. But why a stable and why unstable equilibrium? See, imagine this. If I give you 3 cups, something like this. Okay, not 3, 2 cups. In one case, this is a cup and in the other case, this is a cup. Take a ball here and take a ball here. In this case, if you push the ball, after you release the ball will just come like this and finally stabilize it at the original position itself. But over here also, with a lot of difficulty, you can actually stabilize the ball here. It will be in equilibrium only. But if you give it a slight push from here, the ball will start rolling down. So this condition is what you call stable equilibrium. It never comes back to the original position after you give it a slight push from the equilibrium position. And after you give this ball a slight change from the equilibrium position, it will get back to the equilibrium position here. So this is what you call stable and this is what you call unstable equilibrium. Now why do I say this is stable and this is unstable equilibrium? Think over it. What if you try to displace it over here? If you try to displace this over here, then the dipole will look like this. In the first case, your dipole will become like this, with the plus charge here and the minus charge here. The plus charge experiences a force here and the minus a force here. So because of these two forces, the dipole will get rotated like this. So initially the dipole was here, you gave it a slight push, the dipole is again trying to come back to that position only. But what if the dipole was this? If the case was this, the plus charge would have been, the plus was here and the minus was here. You give the dipole a slight push like this, then the dipole will now look like this. With the plus charge here and the minus charge here, the plus charge experiences a force here and the minus experiences a force here. Now because of these forces, the entire dipole, the dipole was this, the dipole will now turn completely like this, and that is why it never comes back to the original position after you give it a push from here. So this is a position of unstable equilibrium where P bar and E bar are anti-parallel to each other, whereas if P bar and E bar were parallel to each other, you saw that the dipole was returning to the original position, and that is why this was a position of stable equilibrium. So this is where one more question comes in. In mechanics you have learned that because of inertia, an object which is moving cannot come to stop instantaneously. So when we considered the case of stable equilibrium, we had a dipole like this, we turned it a little and after we release it, the dipole is going to come here. But after it comes here, because of inertia, the dipole cannot stop, and that is why it will keep going ahead. But the moment it goes over here, it will now experience a restoring torque like this. So the dipole will go up. Again, it cannot stop here because of inertia. So the dipole is going to keep performing simple harmonic motion. Okay, it's not simple harmonic motion because simple harmonic motion is in a straight line. But if you realize this is some kind of periodic motion. So because a dipole is going to perform periodic motion after you release it or after you displace it slightly in an electric field, we say that time period of that periodic motion will exist. And time period of that periodic motion is given by 2 pi root over I upon mb or I upon pe. Sorry, mb was the formula that we use in magnetism. Pe is the one that you use for electrostatics or electric dipole. So the time period of the electric dipole will be given by 2 pi root over I means the moment of inertia of that system. The dipole moment that got, or the electric dipole that got generated will be having some moment of inertia because it is rotating or it is oscillating. So that moment of inertia divided by P into E, where P is the electric dipole moment and E is the electric field intensity of the electric field in which you have kept the dipole. So this is yet another formula you should remember. So this is the entire discussion about electric dipole and electric dipole moment. This is where I am done with whatever I wanted to cover in this video. Thank you for watching, guys, and I hope that whatever I have discussed in this video has been someplace somewhere helpful to you in your preparations. Thank you for watching.